All right, so we talked about solids earlier during the review. Well, let's talk about liquids. And the key thing that makes liquids and solids different from gases is the presence of the intermolecular forces. And so an ideal gas has no intermolecular forces. A real gas might have some very minimal intermolecular forces that might affect the properties of the gas very slightly. But when the intermolecular forces take hold and they really bring the particles together through some pretty significant attractions, then the gas will condense into a liquid or a solid. So it's the magnitude of intermolecular forces that determines whether it's going to be a liquid, solid, or gas. It's not just the magnitude, it's also how extensive the network of attractions is. If I have a large molecule, with a lot of surface area, if there's maybe one of these long carbon chains or something with a lot of atoms attached, there's a lot of surface area of that molecule. That's a lot of area where there are electrons and electron clouds shifting around. And so this molecule might form a lot of areas of partial charge and allow it to attract to neighboring molecules. Even though the individual attractions are not that strong, the magnitude of the attractions might not be strong if they're only due to temporary shifting due to London forces. If I've got a lot of them all over the surface at the same time, then I can start to form a lot of connections, a lot of attractions with neighbors. And so it's not very likely that that substance would end up in the gas phase. So it's really the number and the complexity of the network of connections that a molecule can make with its neighbors that's important, as well as the actual strength of each individual attraction and the amount of partial charge or full charge if it's an ion involved in that attraction. So we know in a gas the attractions are non-existent or minimal enough where the particles don't come together and the particles are far enough apart to be kind of acting independently. And then in a liquid, the attractions pull the particles together. It's really the only difference between a liquid and a gas is the extent to which the attractions pull the particles together. And then when I make a solid, usually the attractions are strong enough not only to pull them together but to cause them to organize. And that organization usually allows the particles to make the greatest number of attractions. So when I have a liquid, what are some of the properties or behavior of that liquid that is affected by the intermolecular attractions? One of those properties is called surface tension. Surface tension is a result of the number of attractions a molecule can make on the surface being different from the number of attractions it can make when it's in the bulk of the material. So these arrows here are pointing out that if I just take one of my molecules in the bulk of the material, it's surrounded on all sides by other molecules. So it's forming a lot of intermolecular attraction. The more attractions it forms, the more stable it is. When I compare that to one on the surface molecules are only attracted to the ones below them and on the sides. There's nothing above them. If there's nothing above this surface to form attractions to that molecule. So it's not as stable on the surface. The more attractions it can make, the more stable it will be. The more favored that is for the molecule. So these molecules on the surface are unstable and they're being pulled into the surface of the liquid, pulled down into the bulk where they become more stabilized. Okay, that results in a surface tension. Another way to think about surface tension is to say that because this molecule on the surface is attracted to the other molecules around it, there's a network of attractions connecting these together that makes it difficult to penetrate the surface of the liquid because these attractions hold the molecules on the surface close together. It's kind of like a wall or a network, and they're all being held in to the bulk by these attractions pulling them all down. So if you want to break the surface of the liquid, you need some force. Surface tension is a property that allows boats to exist. And so if I have a boat and I put it on the water, it doesn't sink. Even a boat made out of steel, like a battleship. Right? Steel is very dense. It doesn't sink though because of the amount of water it displaces. And so if I have something with a large surface area and I put it down on the surface of this water, or whatever this liquid is, the more surface tension the liquid has, the more the liquid molecules attract one another, the harder it's going to be for me to penetrate that surface. Because if I penetrate the surface, I have to break a lot of those attractions. If I have something that's very narrow, and I put it in the liquid this way and kind of slice the liquid, to do that, it's very easy to break through, because in that case, I only have to break a couple of attractions between the particles to allow that substance to penetrate the liquid. But if it's flat and it has a large surface area, now it can't break through, because to break through, it would have to break a whole bunch of attractions. And so the attractions between the particles create surface tension. Not all liquids have the same amount of surface tension. Right, so here's a big thing for liquids that's different than for gases, because when we talked about gases, we said when we use the ideal gas law, it doesn't matter whether we're dealing with nitrogen or oxygen or chlorine or what the gas is. If it's following the ideal gas law, the behavior of the gas is independent of what the gas is made up of. But the behavior of a liquid is not independent of the identity of the substance making up the liquid. Because in a liquid, if you have water versus something that's not very polar, there's going to be a big difference in the quantity and strength of the attractions between the particles. So the properties of the liquid are highly impacted by the identity of the substance that makes up that liquid. Another way you can think about surface tension is to think about when you have droplets of water, the way that they beat up. Right? So why does water form a droplet? Like we know if we have a drop of water, it forms like a teardrop shape because of gravity, but if you don't have any gravity and you had a droplet of water, it would be spherical. Why are droplets of water basically spherical? Yeah, the surface tension pulls the liquid in, right? The molecules on the surface are less stable than the ones in the bulk. So the shape that allows the most molecules to be in the bulk of the material and the fewest molecules on the surface is a sphere. That makes overall that droplet of water as stable as it can be, because there are the maximum number of particles in the bulk compared to how many are on the surface. And then another way to think about it is, all these ones on the surface are being attracted to the bulk by these intermolecular forces, and they're being held in and attracted, so that pulls them all in equally on all sides and creates a sphere as a result of that. So one way to measure surface tension is to take a flat surface and put a droplet on the surface. If I have a liquid that can't form very strong intermolecular attractions and I put a drop of that on the surface, then gravity will kind of flatten that drop out. If I have a molecule or a sample of a liquid with molecules that attract really strongly, and those attractions create some more surface tension, then when I put a droplet on that, it will ball up more. And so I can measure what is the angle here between the flat surface and the angle created by that droplet versus the angle on the flat surface here and the angle created by that droplet. The larger the angle, the more surface tension the liquid has. Because of the attractions pulling the liquid, into the bulk rather than allowing it to flatten out. Any questions about that? Okay, so that's one property of liquids you should be able to explain and describe based on the intermolecular attractions. Another property is called capillary action, and that has to do with cohesive forces. Adhesive forces. So the adhesive forces are the forces that attract a molecule to something else. For example, when I have glass and I put water in my glass, I get this meniscus, right? So the liquid in the water, the surface of that liquid forms like a dip there called the meniscus. Why does it do that? Yeah, something is attracting the water to the glass. Why would water be attracted to glass? The water is polar, and so if it's attracting the glass, it must also be polar, right? Yeah, glass is very polar. Glass is made of silicon-oxygen bonds. And so what's in glass, all these silicon-oxygen bonds. Silicon has an electronegativity of 1.8, and oxygen's electronegativity is 3.5. That is a huge difference. These are extremely polar bonds, and I'm going to end up with very large quantities of partial positive and negative. Larger than the ones even in water, because the electronegativity difference there is less. So yeah, the water molecules attract one another and create surface tension, but they attract the glass even more. So those attractions between the glass, those intermolecular attractions, pull the liquid up against the force of gravity, overcoming gravity to an extent, allowing the water to move up the glass. And that's called capillary action. So when you have a liquid that's attracted to some solid through these intermolecular attractions, the liquid moves up the solid, that's called capillary action. You do the same thing at home. You take a towel, fill up your sink with water, take a towel, and dip it in the water just so that the end of the towel is in the water. What will happen? Yeah, the water moves up the towel. That's capillary action. Eventually, the whole towel will be wet if you wait long enough. I would probably work on those practice questions from the textbook rather than doing that experiment, but the water molecules are attracted to the towel. What's the towel made up of? Cotton, probably. And cotton is made up of this cellulose and other plant sugars and long chains of carbons and oxygens and hydrogens, and those molecules can hydrogen bond, and so the water molecules attract to the towel molecules through these hydrogen bonds, and they move their way up through that capillary action. So that's another property of liquid. So when a liquid has adhesion and is attracted to some other surface, it will move up that surface at least somewhat through capillary action against the force of gravity. So when the substance, though, is more attracted to molecules of the same type than it is to the surface, then I get the opposite effect. So if I put mercury in a glass, instead of forming a meniscus the traditional way, it forms like a reverse meniscus, and I get this mound of mercury at the top. And so that's because the mercury atoms attract one another better than they attract to the glass. The mercury atoms are not that polar, right? They're just individual atoms of mercury. But where is mercury on the periodic table? It's way down near the bottom. It's got electrons all the way out to and including the 6th energy level. So these are very fluid. And when one mercury gets next to another mercury, their fluid electrons shifting around create really significant partial charges. So this is like really powerful London forces, and those London forces attract the mercury atoms to one another a lot better than they even attract to the polar glass. And so that creates this cohesion where the mercury attracts other mercury. And so that's another property of liquids that you want to be aware of. So that's also a kind of a type of capillary action. Yes. Yes. Yep.
Why is that?
Because of the London forces that the mercury creates. So, if you think about, this large atom with so many layers of electrons, the electrons can shift around. And when they shift around temporarily and create partial charge, that will induce another mercury atom to shift its electrons and create partial charges. And they create really significant partial charges, even though they're not naturally polar, because their outer electrons experience so much shielding by the inner electrons and they're pushed so far out. They shift around really a lot, and they're very fluid, and it creates a lot of really significant partial charges. It can, but just not as much as it attracts to the other atoms of mercury. If you had something similar with the ability to form another substance present with similarly large atoms that could shift around and create similar London forces, then it would probably be able to mix together with those atoms. But the silicon and oxygen are much smaller, and they don't have the London forces that the mercury has to the same degree. Another property of liquids that's impacted by their intermolecular attractions is viscosity. And viscosity is much more about the network of attractions versus the actual strength of the individual attractions. The network that it can form is much more important. And that's illustrated well by the glycerol molecule. So viscosity is a tendency to resist flow for a liquid. Right? So a lot of liquids, we call them, they're like thin. They flow really easily. If I have acetone or water in a glass and I pour it, it just falls right out. It flows out of the glass, no problem. If I do the same thing with glycerol and I hold it upside down, it's like molasses. You could say it's thicker. Really, you should say that it has a lot more viscosity. And it flows out very, very slowly. Very, very slowly. And the reason for that, I mean, if we look at glycerol versus ethanol, the molecules are pretty kind of similar. They have the same elements present. So that's glycerol there. Ethanol looks like this. They're both capable of the same type of hydrogen bonding. And so when I have a sample of ethanol, all the molecules look like this. They have areas of big partial charge. They can attract to a hydrogen bond. I make the same argument for that I can make about two molecules of glycerol. So what's the difference? Why is one so much more viscous than the other? It has to do with the number of attractions that it can make, not really so much with how strong those attractions are. Because water has, or ethanol has the capability of forming 3 hydrogen bonds. The oxygen's large partial negative on each one of those lone pairs can form a hydrogen bond with another molecule, and the large partial positive can form a hydrogen bond with another molecule. The area of carbon and hydrogen have only minimal electronegativity differences, so they're not having large partial charges, only minor partial charges, so they can't really hydrogen bond. So this ethanol molecule can form up to 3 hydrogen bonds. And so if it's in the sample and it's forming some hydrogen bonds with the neighboring molecules, there's only 3 of them. A little bit of motion is all it takes to break them and allow the ethanol molecule to flow away. So the liquid is a low viscosity liquid. It flows readily. But the glycerol has 3 OH groups on every molecule. So each oxygen can form up to 2 hydrogen bonds, and each hydrogen can form a hydrogen bond. So that's up to 9 hydrogen bonds at any moment. And so when this glycerol molecule is surrounded by other molecules, it might have attractions to up to 9 neighboring molecules at the same time. And so in order for it to flow past the other molecules, it would have to break all those attractions. And that's not nearly as likely. So it's hard for the molecules to flow past one another when they have a lot of individual attractions with their neighbors. That's an extensive network of attractions with the neighbors is the key thing to viscosity. And I could take a oil, like olive oil. It's thicker than water, right? It doesn't flow as readily as water. It's more viscous than water. Not because the oil molecules form stronger attractions, because the oil molecules are nonpolar and they don't form strong attractions, they form weak London force attractions. But the oil molecules are long chains and they form lots of areas of small partial charge along the chain, so they can form a larger number of attractions with the neighbors rather than stronger individual attractions. So it's the number of attractions, the extensiveness of the network of attractions that really affect viscosity. Vapor pressure is another property of liquids that's really important. So vapor pressure has to do with the pressure of a gas created over the surface of a liquid as the liquid evaporates. So let's come back to this. We'll talk about the visual picture that shows vapor pressure real quick. So to measure vapor pressure, I freeze a liquid, I put it in a container with the vacuum, and I pump out all the gas. And so there's no gas above this liquid. The liquid is frozen. I have mercury in a tube so I can measure the pressure of the gas once there's gas created. Right now there's no pressure. There's no pressure of the gas hitting down and pushing that mercury up, so the level of the two sides of the mercury is the same. Then I heat up the liquid, or heat up the frozen liquid until it melts. And I hold it at a certain temperature. So vapor pressure has to be measured at a certain temperature. I've got to keep it at that constant temperature to measure vapor pressure. So I keep it at a certain temperature. Slowly, some of the liquid starts to evaporate. As the liquid evaporates, I have some amount of gas forming. As more liquid evaporates, eventually I reach a point of equilibrium, where still some of the liquid molecules, which maybe are moving slowly, will have some other molecule collide with them, and they'll be moving a lot faster, and they'll break their intermolecular attractions and escape and become part of the gas. Meanwhile, particles in the gas, which are moving fast, might collide with something else and transfer that motion. They might start moving slower. And if they're moving slower and they come in contact with the liquid, the intermolecular attractions will pull them into the liquid. So equilibrium is reached when the rate of evaporation is the same as the rate of condensation, because I have those things happening at the same time. At that point, whatever the quantity of gas is, those collisions of the gas particles bouncing around will hit down on this mercury and push it up the tube, and I will get a certain height. Right? And we know that the height at which mercury is pushed up the tube relates to the pressure of a gas. That's what vapor pressure is. So vapor pressure is the pressure created by gas that is present because some of a liquid evaporated. Right? And this is a property of a liquid. Some liquids at room temperature have a high vapor pressure. Other liquids at room temperature have a low vapor pressure. So is it correct to say that if a liquid has stronger intermolecular attraction at room temperature, it should have a high vapor pressure? No, that's not correct to say. Vapor pressure has to do with how much gas there is, and so the more gas I create, the more pressure there will be, right? Pressure for a gas is related to the number of moles and the temperature and the volume. And so the more moles evaporate, the more pressure created by the collisions of those gas particles. So if the attractions between the particles of the liquid are strong, if the intermolecular attractions are strong and it holds the liquid together, there will be less evaporation and the vapor pressure will be lower. So once I reach this equilibrium, depending on the strength of intermolecular attractions in the liquid, if there are strong attractions, I'll have fewer moles of gas and a lower pressure. If I have weak attractions between the liquid, I'll have more evaporation when I get to equilibrium, and more moles of gas and a higher pressure. The vapor pressure also is affected by temperature, though. So let's say, I have at a certain temperature, I'm looking at the energies, the kinetic energies of the particles. We know that temperature is a measure of the average kinetic energy. Right? So if I have a low temperature, that means on average the particles are not moving that fast. There's some moving still pretty fast and some moving pretty slow. And I have this distribution of speed. Right? So the higher up here on the y-axis, the more molecules I have at that certain speed. So when I'm at a certain temperature, there are only a few molecules moving at the speed necessary to break their intermolecular attractions and escape the liquid and become part of the gas. Most of the molecules at a low temperature on average have a low speed. When I increase the temperature, I still take this same shape, but I just stretch it out. And so now at a much higher temperature, the molecules that are moving with enough speed to break their intermolecular attractions to become a gas. There's just a lot more of them that have that speed. I still have some that are moving very slow, so I'm never going to see like an instantaneous evaporation of all the particles at once. No matter what temperature I'm at, I'm never going to have a situation where all the molecules at that instant in time are moving fast enough to break all their intermolecular attractions and everything evaporates instantly. Because there will always still be some that are moving slow enough to hold their intermolecular attractions together to stay as a liquid. So over time, slowly evaporate. But what we're saying here is the higher the temperature, the more this distribution of speed broadens out, and the more molecules I have moving fast enough to break their intermolecular attraction. So I get more molecules in the gas state and a higher vapor pressure that results from that. So we know the vapor pressure is affected by temperature, so these curves kind of show that for 3 different substances. So if you take a look at water, so if I'm at 0 Celsius and the water is frozen, the vapor pressure is basically 0. Right? Frozen, the particles are stopped. They can't even flow past one another. None of them have the speed necessary to break their intermolecular attraction and become a gas, so I don't get any vapor pressure resulting from that gas. But as I slowly increase the temperature, the vapor pressure starts to go up. Right? Higher temperature, more of the molecules are moving fast enough to break free of their hydrogen bonds and evaporate and become part of the gas. And so what I see here is that when I get to 100 degrees Celsius for water, the vapor pressure is equal to 1 atmosphere. That's what boiling point is. So boiling point is not technically the temperature at which the sample starts to evaporate. Because we could be at room temperature and it's still evaporating. There's still some vapor pressure. The boiling point is the temperature at which the amount of liquid that's evaporated creates enough pressure to be equal to the atmospheric pressure around it. Right? So if you have a liquid in the room and there's atmospheric pressure hitting down on the surface of that liquid, the liquid has to be hot enough where the vapor coming off the liquid creates a pressure equal to the atmospheric pressure pushing down on it in order for you to actually start to see boiling. So we can measure, we can recognize that the vapor pressure and the boiling point both depend on the intermolecular attraction. The stronger the intermolecular attractions, the lower the vapor pressure at a given temperature. The stronger the intermolecular attractions, the higher the boiling point, because it will require higher temperature to get the vapor pressure to become equal to the atmospheric pressure. Any questions about that? That's what? Yeah, right. If you're boiling water in order to cook some food, but you're at a high altitude, the water will boil at a much lower temperature because normally water needs to get hot enough so that enough molecules of water evaporate and become a vapor with a pressure of 1 atmosphere. That takes a lot of energy to get that many molecules to evaporate and to create a pressure of 1 atmosphere from all the gas that's evaporated. But if your atmospheric pressure is much lower, then it doesn't take as much energy to get the water to boil because it will boil at a much lower temperature. It only needs to produce a lower vapor pressure to equal the atmospheric pressure to get to the boiling point. So it takes a lot longer for your food to cook, or might not cook in the same way if the water that's boiling that's meant to cook the food is boiling at a much lower temperature. Yeah, you can also get water to boil. I mean, if you connect the water to the vacuum line in the hood and heat it up, water wouldn't, but some other liquids with lower boiling points would start to boil at room temperature under a vacuum. So you get that. That's one way to quickly evaporate a liquid that you want to boil off without heating it so much, is to put it under vacuum. Let's look at some of these questions from the textbook. Make sure we have all the key points here. So I wanted to talk about 7.34. That relates to some of these concepts, specifically boiling point. So before we talk about solids, so in 7.34 we've got 4 substances it gives us, and we're meant to rank them in terms of strength of attractions, which relates to their boiling points. So what's the biggest factor that affects the boiling point of a substance? Oh, it's so quiet in here now. Yeah, the strength of the intermolecular forces, right? So which of those should have the highest boiling point? I want to look at the shapes of these molecules and see which ones have the strongest see which ones have the largest quantities of partial positive and partial negative. So for this RBF, this one you should recognize as ionic. Right, the RB is here. It's not going to be sharing electrons. It's going to give away one and become a positively charged ion with the same number of electrons as a noble gas. And so when I have a metal and a non-metal, they usually will have opposite charges. That's a really strong attraction, full charge attraction. So it's going to take a really high temperature to break that attraction and separate those ions. So this should be the highest boiling point. Looking at the CO2, I've got a nonpolar substance, so that should only have London forces. Looking at the CH3OH, the OH specifically creates some big electronegativity differences. That can do some hydrogen bonding. The CH3Br only has a minimal difference in electronegativity, so that's only going to have some minimal dipole-dipole attraction. So if I can find a difference in the type of attractions, that gives me the information I need to rank them. Right, so the ionic bonds here are a very strong attraction. The hydrogen bonds are less strong than the dipole-dipole because of the polarity there is less strong, and the London forces only are probably the weakest. So that allows me to rank. This would be the highest boiling point, then here, then here, then here. And so the key thing there, we have to apply the skills we learned before the last exam. You have to have a reasonable Lewis structure. You have to be able to show that basically the shape and the areas of where atoms are bonded together that's going to create large partial charges if you want to predict how those partial charges are going to affect the properties of a substance, like boiling point, viscosity, surface tension, all those things. Let's look at 7.36. So here we're looking at boiling point as well. This one's a little bit different of a question though, because here we're given 3 pairs, so the analysis for any one of those 3 is pretty much the same. So let's just look at one, O2 versus Cl2. If we want to predict what is going to have a higher boiling point, we'll look at the types of attractions. If you run into a situation, though, where they experience the same types of attractions, so I've got 2 molecules here, both of which the best type of attraction they can make is London forces, then I want to look at either how many attractions can they make with their neighbors, how extensive will their network of attractions be with their neighbors. That's not going to make a difference here because they're both basically the same size, just 2 atoms connected together, so the number of attractions they can make with the neighbors will basically be the same. So what's the difference? How can I find a difference between them? Yeah, the fluidity of the electrons are in the electron clouds in the atoms. That's what I want to look for. So if they have the same types of attractions and a similar degree of number of attractions they can make with neighbors, then I want to look to the London forces. This relates to one of the questions on the last exam. In this case, these two should both experience London forces, but the chlorine is a larger atom than the oxygen. It has a whole other layer of electrons. Its valence electron should be much more fluid. It should be able to create stronger London forces than the weaker London forces of the O2. And so this one should have the higher boiling point. You can make the same argument for parts B and C there for that as well, except in part C, let's just look at that real quick. In part C, you have HF versus HI. So the HI should have a much larger electron cloud than the fluorine. And so in the HI, even though at best it can form dipole-dipole and London forces, the London forces should be very significant because of the size of the iodine and the fluidity of its electrons. However, the HF can also form hydrogen bonds because even though the fluorine is small, there's a huge electronegativity difference between fluorine and hydrogen, and so that's going to create huge partial charges versus the small partial charges on the HI. So in a situation like that, you want to first look to the types of attractions that can form as the key factor rather than the London forces. So London forces are a secondary part of that analysis. Right. Yeah. Yep. All right. Let's look at 12.1. A couple more details about liquids here. Explain why liquids, unlike gases, are virtually incompressible. Well, the liquids have intermolecular attractions that hold the particles already really close together. There's no empty space between them, really. Very little. So you can't really compress a liquid into a smaller volume than it normally occupies because the particles are already pretty much as close as they can get. They're already held as close as they can get by the intermolecular attraction. So if you did try to compress a liquid, you'd have to actually start overlapping one molecule on top of another molecule, and that is going to be a huge amount of repulsion as the like charges start to get close together. So you can't really do that. So gases are compressible because there's a lot of empty space. Liquids don't really have much empty space, so they're not really compressible. 12.3. Despite the fact that stainless steel is much more dense than water, a stainless steel razor blade can be made to float on water. How is that? Yeah, surface tension. Right. So if you take the razor blade like this, it will cut right through. But if you flatten it and you're very careful with how you place it on the water, it could float on top of the water. Not because it's less dense and it actually is supposed to be floating, but because when it's a light, it's not very heavy, and it's flat, it can't break through the surface because all the water molecules on the surface have these hydrogen bonds connecting them together, and it's hard to break the network of attraction with the razor blade placed on top of the water in that way. So it's all about surface tension. 12.7. What is viscosity? What is the relationship between intermolecular forces and viscosity? So as we said, viscosity is the resistance for flow. It has to do with an individual molecule's ability to slide past the other molecules around it in the liquid. And as we said, that's primarily impacted not as much, somewhat, but not as much by the strength of the attractions the molecule can make with its neighbors, but more affected by the number of attractions it can make with a greater number of neighbors. And if I have two particles in the liquid that have lots of attractions with one another, I don't necessarily have to break that for the liquid to flow. Those two could stick together, continue to attract, and still flow around as a team through the rest of the liquid molecules. And so that's not going to be that much of a viscosity. But if a molecule forms attractions with a bunch of molecules all around it on all sides, then the ability for that to flow around is going to be really, really restricted. It's going to be much more viscous. So it has to do with how extensive the network of attractions are between the molecules. Is the main thing with viscosity.